Hello, my dear friends, and welcome to our astronomy course. Okay? Today we have uh, lecture number 12, and the topic of our lecture, we will be continuing study the terrestrial planet. You know, when Earth was young, its atmosphere had no free oxygen. That is, oxygen not combined with other elements. Oxygen is very reactive and quickly forms oxidized in the soil. Plant life is what keeps a steady supply of oxygen in Earth's atmosphere. Photosynthesis makes energy for plants by absorbing carbon dioxide and releasing oxygen. Beginning about 2 to 2.5 billion years ago, photosynthetic plants in the ocean had multiplied to the point where they made oxygen. Oxygen at a rate faster than chemical reaction could remove it from the atmosphere. After that time, atmospheric oxygen increased rapidly. It is a common misconception that there is life on Earth because of the oxygen. The truth is exactly the opposite. There is oxygen in Earth's atmosphere because of life. Most life forms on Earth do not need oxygen, except, except the minority of creatures that are animals. And some are even poisoned by it because there is oxygen in the atmosphere. Now, there is also a layer of ozone, O3, or O, atomic oxygen, at altitudes of 15 to 30 kilometers. Many people have a common misconception that ozone is bad because they hear it mentioned as part of pollution. Breathing ozone is in fact bad for you, but you need the ozone layer in the upper atmosphere to protect you from harmful solar ultraviolet ozone. Certain compounds called chlorofluorocarbon, CFC, chlorofluorocarbon, used in refrigeration and some industrial applications can destroy ozone when they leak into the atmosphere. Since the late 1970s, the ozone concentration in the upper atmosphere has been falling, referred to as an ozone hole. I hope some of you hearing about this. Yes? Okay. And the intensity of harmful ultraviolet radiation at Earth's surface, especially at high latitudes, has been increasing. There is yet another common misconception that global warming and ozone depletion are two names for the same thing. Take careful note that the ozone hole is a second Earth environment issue that is basically separate from global warming. While ozone depletion poses an immediate problem for public health on Earth, it is also of interest astronomically. When you visit Mars, you will see the effect of an atmosphere without ozone. What evidence indicates that Earth has a liquid metal core? A good scientific argument focuses on evidence. It's reasonable. It's one part of science. You know, in this case, the evidence is indirect because you can never visit Earth's core. Seismic waves from distant earthquakes pass through Earth, but a certain kind of wave, the S-type, does not pass through the core because the S waves cannot move through a liquid, and so scientists conclude that Earth's core is partially liquid. Earth's magnetic field gives further evidence of a metallic core. The theory for the generation of magnetic fields, the dynamo effect, requires a moving, conducting liquid for a planet or gas for a star in the interior. If Earth's core were not partially a liquid metal, it would not be able to generate a magnetic field. Two different kinds of evidence tell you that our planet has a liquid core. Can you build a new argument? What evidence can you cite to support the theory of plate tectonics? And now let's review about terrestrial world. The terrestrial world differ mainly in size, but they all have low density crust, mantles of dense rock, and metallic core. Earth's moon is included in this study because it is a complex world and illustrates important principles such as cratering and flooding by lava. Comparative planetology leads you to expect that crater surfaces are all that heat flowing out of a planet drives geological activity, and that the nature of a planet's atmosphere depends on both sides of the planet and its temperature. Earth has passed through four stages in its history. First, differentiation. Second, cratering. Third, flooding by lava and water. And fourth, slow surface evolution. The other terrestrial planets plus Earth's moon have also passed through versions of the same four stages. Also, the relative importance of the stages differs from object to object. Seismology, especially tracking the path of earthquake, P waves, and S waves, shows that Earth has differentiated to form a metallic core that is partially liquid. The metallic liquid outer core generates Earth's magnetic field. Earth is dominated by plate tectonics that break the crust into moving plates, driven by heat flowing upward from the interior. The crustal plates float on dense mantle rocks that are described as plastic because they slowly flow under pressure. Evidence of plate tectonics includes rift valleys, middle ocean rises, subduction zones, and older mountain ranges. Near crust is mostly created at middle ocean rises as a type of volcanic rock called basalt. Earth's primary atmosphere was probably mostly carbon dioxide, but that gas mostly dissolved in water. And plant life has released oxygen, creating the present secondary atmosphere. And that's very nice, right? Gases such as carbon dioxide, methane, and water vapor trap heat in the Earth's environment, called the greenhouse effect. Without the greenhouse effect, Earth would be uninhabitable, with an average temperature well below freezing. Human burning of fossil fuels has significantly increased the amount of carbon dioxide in Earth's atmosphere, causing a noticeable rise in average temperatures called global warming. Those moons form in a mostly molten state and differentiated, but it contains little matter and has an overall low density. Those moon is a small ball and so has lost most of its internal heat and is no longer geologically active. Its old highlands are heavily cratered, but the lowlands are filled by lava flows that form smooth maria, singular mass. Soon, after the end of the heavy bombardment, the overall reflectivity or albedo of the moon is very low, even in the relatively bright highlands. The moon's surface is fractured by impacts, producing craters that are especially easy to see near the terminator, the moving boundary between the sunlit and unlit part of the moon. The terminator line is a line between the sunlight and dark space because it's very distinctive line because the moon hasn't the atmosphere. Okay, debris blasted out of craters is called ejecta and can produce secondary craters. Impacts have resulted in prominent features such as crater rays and multi-range phases. Lunar rocks brought back to Earth include vesicular basalts from parts of the moon where the surface was covered by the successive lava flows. Anorthosite, which shows that a large portion of the moon was once a magma ocean, and breccia, providing evidence that the moon has been repeatedly pounded by impact. Mercury is smaller than Earth, but larger than Earth's moon. It is airless and has an old, heavily cratered surface. Mercury has a much higher density than Earth's moon and must have a large metallic core. Mercury may have suffered a major impact that blasted away from low density crustal rock and left it with a metallic core that is large in proportion to the diameter of the planet. Lobate scrubs along thick carving cliffs formed by compression on Mercury when its large metallic core solidified and contracted. Venus is almost as large as Earth. It has a thick, cloudy atmosphere of carbon dioxide that hides the surface from sight. It can be studied by radar mapping. Venus' carbon dioxide atmosphere drives an intense greenhouse effect and makes the planet's surface hot enough to melt leaves. Venus is slightly closer to the sun than Earth, too warm for liquid water oceans to dissolve carbon dioxide from the atmosphere easily, and warm enough to start evaporating its ocean, leading to a runaway greenhouse effect. The hot crust of Venus is not dominated by plate tectonics, but rather by volcanoes and vertical tectonics, including corona, large circular uplifted regions. Crater counts show that the entire surface of Venus has been covered over or replaced in the past half billion years. Composite volcanoes are associated with subduction zones and plate boundaries on Earth, whereas shield volcanoes found on Earth, Venus, and Mars are caused by rising columns of magma called hotspots that break through the crust from below. Mars is about half of the size of Earth. It has a thin atmosphere and has lost much, but not all of its internal heat. The loss of atmospheric gases depends on the size of a planet and its temperature. Mars is cold, but it is small and has a low escape velocity, and thus many of its lighter gases have leaked away. Some water may have leaked away from Mars as ultraviolet radiation from the sun broke it into hydrogen and oxygen. But some water is frozen in the polar caps and as permafrost in the soil. One of these places of frozen water you may see on the pole, on the top of this figure. Okay? Outflow channels and valley networks visible from Mars orbiters seem to have been cut by sudden flood or by longer-term drainage. But water cannot exist as a liquid on Mars now because of its low temperature and low atmospheric pressure. Therefore, conditions on Mars must have once been different, allowing liquid water to flow on the surface. The southern hemisphere of Mars is all crater terrain, but some large volcanoes lie in the north. The size of these volcanoes strongly suggests that the crust does not move horizontally. Some volcanoes may still occur on Mars, but because the planet is small, it has cooled and is not very active geologically. Orbiters have found evidence of large amounts of water frozen below the surface. Rovers have found clear signs that Martian climate was different in the past and that liquid water flowed over the surface in at least some place. The northern lowland may even have held an ocean at one time. The 2 moons of Mars are probably captured asteroids. They are small, airless, and cratered. They lost their internal heat long ago. And now we begin to next part of our lecture. We start in lecture the topic of the Jovian planet, Pluto, and the Kuiper belt. You know, in the last 2 lectures, you watched our solar system form and explode the terrestrial planet. Now, you can explore the outer solar system. The Jovian planet will be a challenge to your imagination. They are so unearthly. They would be unbelievable if you didn't have direct observational evidence to tell you what they are like. Nevertheless, the concepts of comparative planetology will continue to be faithful guides. The planets of the solar system form from small bodies in the solar nebula. To some extent, the planets are still affected by those small objects. In the next lecture, you will adapt your understanding of comparative planetology to study the last remains of the solar nebula, meteorites, asteroids, and comets. What practical value is there in sending a space probe to Saturn. Sending spacecraft to another world is expensive, and it may seem pointless when that world is hostile to human life. To resolve that question, you need to consider the distinctions among science, technology, and engineering. Science is simply the logical study of nature. Also, much scientific knowledge proves to have tremendous practical value. The only real goal of science is a better understanding of how nature works. Technology, in contrast, is the practical application of scientific knowledge to solve a specific problem. People trying to find a faster way to paint automobiles might use all the tools and techniques of science. But if their goal has some practical outcome, you would more properly call it technology rather than science. Engineering is the most practical form of technology. An engineer is likely to use well-understood technology to find a practical solution to a problem. Of course, there are situations in which science and technology blur together. For example, humanity has a practical and urgent need to solve the HIV and AIDS problem. The poor needs a cure and methods of prevention. Unfortunately, scientists don't understand HIV itself or viruses in general well enough to design a simple solution. And thus, much of the viruses, especially last one, if you remember, was several years ago, right? And it's still active influence to the humans now too. And the research work involves going back to basic science and trying to better understand, in general terms, how viruses interact with the human body. Is this technology or science? It's hard to decide. You might describe science that has no immediate practical value as basic science or basic research. The exploration of worlds, such as Saturn, would be called basic science. And it is easy to argue that basic science is not worth the effort and expense because it has no known practical use. Of course, the problem is that you have no way of knowing what knowledge will be of use until you acquire that knowledge. In the middle of the 19th century, Queen Victoria is supposed to have asked physicist Michael Faraday, what good is experiments with electricity and magnetism worth? And he answered, Madame, what good is a baby? Of course, Faraday's experiments were the beginning of the electric age. Many of the practical uses of scientific knowledge that fill the world, computers, vaccines, plastics, began as a basic research. Basic scientific research provides the raw materials that technology and engineering use to solve problems. Basic scientific research has yet one more important use that is so valuable it seems an insult to refer to it as merely practice. Science is the study of nature. And as we learn more about how nature works, we learn more about what our existence in this universe means for us. The seemingly impractical knowledge gained from space probes, to other words, tell us about Earth. and our own role in the scheme of nature. Science tells us where we are and what we are, and this knowledge is beyond science. The next lecture will be the Jovian planets, Pluto, and the Kuiper belt. And now, I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye. Bye.